Hello and welcome to another video. Today we're going to be working on search a 2D matrix. So in this problem you're given an n by n matrix and it has the following two properties. Each row is sorted and the first integer of each row is greater than the last integer of the previous row, meaning for like this integer is greater than this integer, this integer is greater than this integer, and so on. And you need to be given a target, return true if the target is in the matrix, and false otherwise. You must write a solution that's O of log n by n, so a logarithmic time complexity here. And in this example, we're looking for 3, and we do have it, so we return 3. And in this example, we're looking for 13, and it's not there. So I'm going to show you two ways you could do this, and they're actually going to be the same time complexity, even though you might not think they are, but I will show you that they are. So let's focus on this problem here. Let's actually focus on a sub-problem. So let's actually get rid of this example 2 over here. Let's just get rid of that because we don't really need that. Like, that's just pretty straightforward. Let's actually focus on this one over here. So how do we approach this problem? And let's actually break it down into a smaller problem. So let's say we're just asked to find a number in a sorted array. Like, we just have like 1, 2, 8, 15, 19, and so on. And we're asked to find like number 7. So how do we do this? This should be pretty straightforward for you, that you can binary search, right? So we can just have a left and a right, and we can just binary search to find the middle. So what will happen is, we'll just do another color here just to quickly show you a quick demo. Essentially, we're gonna have a left and a right, and then every time we're gonna find a pivot, and we're gonna say, okay, is our pivot greater than or equal to the number, or is it that number? If it's greater, then let's remove this section. If it's less than, let's remove this section. And if it's equal, let's just say we found it, right? And we're essentially like making this smaller and smaller and smaller and smaller. So for example, here, we're going to remove this section. The right's going to be over here. And then our new pivot will be this value. And now this is smaller. So we're going to remove this section. So now the left and the right are going to be this value. And then both of these aren't going to be 7. And now we're out of bounds. So that's like a rough binary search. So we know how to do this. But how do we transform this into this, right? And I guess the brute force, quote unquote, for this problem is a pretty straightforward one. You can literally just you can just do a matrix traversal, value by value. So this would be like, the first value to visit, the second value, the third value, the fourth value, fifth value. Let's just label all these because we are going to use this for something else. So we can do something like this, right, where it's 10, 11, we can do a traversal, and we can just build up an array of all of these values. So what would that look like? Well, that's also going to be pretty straightforward, so I'm just going to type them out and maybe use a bigger font to show that, I guess. So let's do that. Whoops. Okay, let's use an extra large font, and let's just say, so this is going to look something like 1, 3, 5. I'm actually going to not show the columns just to make it easier. So 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. So now that we have this array, we actually can just do a binary search here, right? This is basically this problem here, and it's the same exact thing. So what's going to be the time complexity and like the space for this one? So for this one, the time is going to be O of n by m still, because you are taking every single number, right? So like this is 12 numbers, so it's still, it's not O of n by m, it's O of log n by m, because you're doing a binary search in an array length n by m. But we also have space O n by m, which is an issue, right? So we created an array. And do we actually need to create this array? Well, let's try not to create this array, right? Let's just say we don't need this array. Let's just try to do this maybe in place somehow. And let's try to get an idea of how we can do that. So there's going to be two ways of doing this. So let's get rid of all this. One way to do this is you can actually map this like index to, like, you can just say like, okay, instead of doing this, let's just say I'll make the left 0 and the right 11. And once I get some pivot value, let's call it 6. So this 6 should correspond to this, right? But what is this in matrix terms? So this is, if we can mark these, this is like column 0, column 1, column 2, column 3, and then row 0, row 1, row 2. So this 6 should be row 1 and column should be 2. right? So we need to figure out how do we map that to that. And it's actually doable. And the way you do that is, if you think about it, for the row, every single row is like length, like let's say we also have values for the length of a row and the length of a column. So let's say here, our row is going to be how many values, right? So our row is 4 values, I believe. Or sorry, for row, we need to figure out a number of rows, and for column, we need to figure out a number of columns. So we have 3 rows, and for column, we have 4 columns. So to figure out the row from this, it's pretty straightforward. Every row has column number of entries, right? So like every row has 4 entries. So we can just divide it by the number of columns, right? So we can take this 6 and we could say, okay, let's just take this 6, let's integer divide by the number of columns, which is 4, and then we're going to get the row, and this would be row 1, right? Which is correct. That is row 1. And we could try another row, maybe like this row here. If we take this 11 and we integer divide by 4, we get 2, right? And this is row 2. So this does work for the row. Let's actually get rid of some of this. So let's get rid of some of this, and let's just write this down. So let's get rid of this as well. Okay, so for the row, let's get rid of that as well. Okay, so for the row, it's actually just going to be whatever index it is, integer divide by the number of columns. Okay, what about for the column? Like, how do we get the column? Well, you can see the column kind of resets over and over and over, right? So it's like column 0, 1, 2, 3, then column 0, 1, 2, 3, then column 0, 1, 2, 3. So it resets. So that should give you a hint. If it resets, it's going to be kind of similar. It's actually going to be, the column is going to be index mod the number of columns. And let's try that out as well for just a couple of examples. So let's say we're trying this 11 again. So that would be 11 mod number of columns is 4 here. So this should give you 3, right? So you're going to get 2 and then remainder 3. And that is column 3. Let's try this 6 again. So 6 mod 4 is going to give you 2. So that should be column 2, which is correct as well. So you can actually just map these and then just do a normal binary search where you just say like, okay, let me make my left be 0 and my right be, so what's the last value here? So the last value should actually be rows times columns, right? So rows times columns minus 1 because it's 0 indexed. So in that case, this would be 3 times 4, which would be 12 minus 1, which would be 11. And you can just do a normal binary search just like in an array. And then every time you get an index, you know where to look by using this conversion. So you get some index and you say like, okay, is it, I check this in the matrix, and then, if your thing is bigger, go this way. If your thing is smaller, go this way. And that's basically how you could do that. So what would be the time and space complexity here? So here it would actually be log of n by m for the time. And then for the space, we're doing it in place now, right? We are just converting a number into a row and a column. So we're pretending this is a one-dimensional array, and we're just converting that index into a row and a column. So that's one way you could do it. And now let's show you the other way you could do it, and let's explain how, even though you think it might be different time complexity, it's actually the same. So the other way you could do it is you can actually first find a row and then find a column. For example, let's say we're searching for this number 3. So our first binary search can actually just look through all the rows and find a row. So how's that going to look? Well, we're going to say our left is 0 and our right is the last row in the matrix. We can just get the length there. So our right in this case is going to be 2, right? Because that's the last row. And we can literally, like, let's say when we get to a pivot 1, we can just say, okay, we have a few cases. So either our number is in the row, and how do we check if it's in the row? Well, that's also pretty straightforward. So we have the matrix. So we can literally just say like matrix at the pivot, and let's get the 0 value. So that 0 value should be less than or equal to the target, and the target should be less than or equal to matrix at that pivot row, and then this should be the last value in the row. So in this example, so like let's say we're at row 1, this number here will be 10, and this number here will be 20, and we need to say like, okay, the number we're looking for, let's say we're looking for the 3 again. Let's say the target's 3 here. This 3 should satisfy this. And if it does satisfy this, then we found the row, right? So in this case, it doesn't actually satisfy it. So then we can also check for, is this, and then we can just check for this value here. So if this first value is in the row is greater than the target, then we need to go left. And if this value is less than the target, that means that this value will also be less than the target, because otherwise this would be in here. Because we checked for that, if 10 is less than the target is also guaranteed to be greater than 20, which means we'd go up. So in our example here, we would have a pivot equals 1, and then we would check for this case. We would say like, okay, is matrix P0 greater or less than the target? Well, in this case, it's greater. So then what we need to do is we need to make our right go into the row before that, right? So we're going to say our right is 0 in this case because our pivot is 1. And then for 0 and 0, now then we're going to check row 0. So for this same condition, for row 0 now, matrix row 0, 0 is going to be this number here. So that's going to be 1 is less than or equal to 3 is less than or equal to, and then it's the last number in the matrix. And we can get these in constant time, right? Because we know exactly like how long the matrix is. We can just get that beforehand. So this operation is in constant time. So then we can say like, okay, is this true? Yeah, that's actually true now. So now that that's true, we actually can save our row. So we can just say like, okay, our row is 0, right? And now that we know our row is 0, let's actually do the rest of it. Like we figured out where our row was. Oh, and by the way, so you can set your row initially to like null or something. And then if you went through your binary search and your row is still null, that means you couldn't find a row for your target. That means you're guaranteed not to have, a target. So now that we have a row 0, now that we know it's row 0, it's pretty straightforward. Now we're just looking for the number in the row. So this is just a binary search for this row. And that's pretty straightforward, right? Like our row is always going to be, it's all, like our left is going to be 0, and then our right is going to be, the number of columns minus 1 in this case. So it's going to be like 3. And then we're always going to be searching at matrix row, and then this is going to be the pivot value. And this is just like a normal binary search. So we're just going to like be like, okay, well, let's just say this is our first row. So actually our right should be 2 here. It should be number of columns minus 1. Okay, so our first pivot value, actually, no, sorry. Our right should be 3, yeah. Because we have 4 columns, so it's 4 minus 1, yeah, okay. So this should actually be 3. So our first value, I think, is going to be 1 that we're going to look at with a pivot in a binary search because it looks for the middle value. So for the pivot, if the pivot is like 1 here, we're going to look for matrix row, and then this is going to be value 1, column 1, which is going to be this value here. So we did just happen to find it right away, in which case we can just return true. But that's like the other way of doing it, where instead of breaking it down into a 1D array, you just look for a row and then you look for a column. And what's going to be the time for that? So if you think about it, looking for a row, there are m rows, right? And you can get, so it's actually going to be log m. And then looking for a column, there are n columns, so it's actually going to be plus log n. So you might think like, okay, well, this is log m plus n. The other one was log m by n, so this is faster. Well, actually for logs, log m plus n equals log m by n. It's the same exact thing. So it turns out like this isn't any faster than the array method. It might just be a little bit more intuitive because you like, I look for a row and then I look for a column. That makes more sense to me. But that's essentially what we're going to be doing. So those are the 2 ways of doing it. They end up actually being the same way of time and space. The only bad or quote unquote bad way is turn this into a 1D array first and then do a binary search there, because then you are actually not using constant space. So now we actually do have enough to code it. So let's do that. And we're going to be coding with this second way where we look for the row and then we look for the column. So let's do that. But you can do it either one. I'm just not going to do both. Okay, so let's look for the row and let's look for the column. So first, let's get some variables to get the number of rows and the number of columns, because we're going to need to use those. So we're going to say rows columns is length of the matrix, and then it's going to be length of a row. So a row is going to be like matrix 0. And these constraints are guaranteed to be at least 1 row and column. Otherwise, you can make some checks before then. Okay, so now we need to make a left and a right. So let's just say our left and our right are going to be 0. And then our right needs to be the last row. So it's actually going to be rows minus 1, right? Like if there's 3 rows, we want this to be 2. And then I'm actually going to set row to none. And then I'm going to check after my binary search to make sure that we actually found a value, right? And if not, that means our number isn't in any row, so we can just return false straight away. Now we have a binary search, so we're going to say while left is less than or equal to right. We're going to get a pivot value. So pivot equals left plus right on 2. And now what do we need to do next? So we need to actually check, like, is this pivot in the row, essentially? So how do we do that? Well, so basically we can say, like we talked about in our example, we could say if matrix, and then the current row we're on is actually going to be pivot here. So if matrix pivot and then 0, the first element in the row has to be less than or equal to the target, and then that target has to be less than or equal to the last element in the row in order for it to be in the row. So pivot, and then the last element is going to be -1. So if this is this, that means this is in the row. So we could just say row equals pivot, and we can break out of the loop because we found a valid condition. Okay. Now we are going to copy some of this. So our next case is if matrix pivot 0. So if the first number in the row is greater than the target, that means that the row has to be smaller than the current low we're looking at. So if the row has to be smaller than the current low we're looking at, we need to go left for the current row. Then we need to go left. So to go left, we need to do right equals, or it's going to be right equals pivot -1. That's what we go left. And then otherwise, this is smaller than the target. And if this is smaller than the target, like I said, the target is also greater than this. Otherwise, this would be true, right? So if this is smaller, then the target is also greater than this. That's why you don't have to do both checks. You can just do one check. Okay, so that means that our row is too small and we need to go right. And so in that case, we're going to do pivot +1. Okay. So now we need to actually check, is our row none? So we could say, like, if row equals none, let's just return false because we didn't find a row, right? So now that we found a row, let's actually find the column. So we're going to make a left and a right again, and we're going to set them equal this time to 0 and columns -1. Because, like, if we have 4 columns, the indices of the columns are going to be 0 through 3. And then we're going to have a while loop again. So let's actually make some more space here, just in case we need it. So you could also do this in like a helper function if you wanted to, but it's only doing this once, and the variables are a little bit different in here, so I just decided to do it like this. But you could do it in a helper function if you want to. Okay, so while left is less than right, some of this is going to be the same. So pivot equals left plus right mod2. And then now what are we checking for? So we're actually checking for the value in the column. So it's going to be if matrix. This is always going to be matrix row. We're never changing the row. We're just changing the column. So this left and the right now have to do with the column. We already found the row. So this is going to be pivot equals target. We can return true. Okay. Now, if matrix pivot is, let's say it's greater than the target, so that means the column is greater than the target. So our column needs to be to the left. So if we need to go left, it's going to be right equals pivot -1. So it is kind of similar to this, but we're returning instead of breaking is pretty much the only difference here. And these are a little bit different than these. Okay, so else the left is going to be pivot +1 because we need to be going right. And then finally, we can return false here because if it actually did find the target in the column, it's going to return true. So if you ever do get past this and you didn't return, that means you didn't find it in the column. Okay, so we can try that. Hopefully we didn't screw anything up. Okay. False. So this needs to be uppercase false. Let's see here. Did it actually? I think I need to make this. Oh, here we go. Okay. So it did actually get accepted, and you can see it's pretty efficient. So that did work. And so let's talk about the time and space complexity once again, just really quick. So for the time, we did this binary search, and then we did this binary search, right? So this is, like I said, this is log m plus log n, but that's equivalent to O of log m by n. Same exact thing. So we're not actually, this isn't actually faster. There's like a bunch of tricks you could do with logs that, you know, you might think your complexity is different, but actually when you do the tricks with the logs there, it's exactly the same. So that is something maybe not everyone knows this, so it's good to know. And then for the space, it's actually going to be O of 1 because we just looked in place. We just used like variables for left, right, rows, and columns. But yeah, so that's going to be it for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. It really helps grow it. And I will see you in the next video. Thanks for watching.